Ready to do the final example. So, iron melts a little bit after 1500 degrees Celsius. So you start to go a little bit past that, iron will start to break down and melt into a liquid. So if we've got a car engine made of iron, the absolute hottest we could run that engine would be 1500 degrees Celsius, right? That would probably be, well, okay, first of all, in real life, that would be magical because the oil that's used to lubricate the engine and make sure it runs smoothly would be burned off, completely gone by that. The gaskets involved, charred. The engine would just completely stop working way before 1500 degrees Celsius, but we can definitely see but it'd be hard to figure out what the precise top level would be. But we can definitely see one good place to say that the absolute top value is when your engine turns to a molten slag of iron, right? When it turns just liquid iron, it's no good anymore. So we can say that the top operating heat would be 1500 degrees Celsius, absolute top level for an engine. So that's still higher than we could possibly get in real life, but the absolute highest temperature we could operate an engine at is 1500 degrees Celsius. Okay, if that car engine is running on a 20 degrees Celsius day, what's the maximum efficiency we could get out of it? So remember, the maximum efficiency is equal to, oh, by the way, this guy right here, he's called epsilon. Once again, yet another of our friendly Greek letters, he's epsilon. Didn't say that earlier, but all of our efficiency has been using the letter epsilon. So our maximum efficiency is 1 minus the temperature of the cold sink divided by the temperature of the hot input. So if we manage to run our engine at its absolute highest temperature, which is 1500 degrees Celsius in sort of a ridiculously high temperature, higher than we could ever achieve in real life, but the absolute top we could pull off is 1500 degrees Celsius, then that's going to be the absolute best we could have, because the bigger the denominator, the better the efficiency we can get, right? If we can get this number equal to 0, we've got perfect efficiency. So we want to make a giant denominator and a tiny cold. Well, what's the cold sink going to be? The cold sink, the best we could do would be the temperature around us in the atmosphere, right? We're not able to drive around with a bucket of ice attached to us. Although that's an interesting idea, but in real life we're going to have to deal with a bunch of other things. We've got like the fact that part of the sink is going to be the engine compartment around us. We've got the engine compartment, and that's definitely not going to be fully at room temperature. So we're going to, at best, be able to pull off that 20 degrees Celsius cold sink. So remember, we can't use Celsius, though, when we're dealing this, because it'd be possible to drop Celsius into the negatives, and then this whole formula would get screwed up. We have to be working in Kelvin, since Kelvin's the SI unit. So if we want to make this into Kelvin, we take each of these and we add 273.15. So the cold is going to be 293.15 Kelvin, and the hot in Kelvin is going to be 1773.15 Kelvin. So the maximum efficiency, we plug both of those in, and our maximum efficiency is 1 minus the cold, 293.15 Kelvin, divided by the hot, 1773.15 Kelvin. That comes out to 0.835, which is equal to 83.5%. Now, keep in mind, 83.5% is ridiculously high because there's no way we could get a real-life engine to operate at those kinds of temperatures, right? We tried to get a real-life engine to operate at those kinds of temperatures, kaput. There's no way we're going to actually be able to pull it off without completely destroying and just ruining our car's engine. So real life, we can't get that kind of temperatures. That kind of temperature in the engine is just ridiculous. We're not dealing with the best temperature we could have. You know, it'd clearly be better the way this works for us to be driving around in the winter, right? A colder temperature than 20 degrees Celsius is something we can definitely pull off, but we're not going to do way better. We can't drop more than, like, you know, if we were to manage to drop to negative 80 Celsius, that'd be colder than any day has ever been on Earth, and that'd be only dropping it by 100. The efficiency is just not going to bump up that much more. So 83.5, when we're dealing with this magical super engine, is the best we can do. And to me, at least, 83.5, that doesn't sound that great. That's getting pretty close to a B minus if this were a test, right? So think about this. Efficiency is actually really, really hard to come by in real life. 83.5% is the best this magical engine can do that's able to withstand these crazy internal temperatures. If that's the best we can do for our engine that's magical, and remember, this is not even including things like the friction, the other real-life forces that are going to occur. This is this theoretical maximum for an already magical engine. So if we were to introduce a little bit of real life, those numbers are going to start to plummet. in real life, for an actual car engine, the theoretical amount that they can put out, so the theoretical for a real car engine operating in real temperatures, so a theoretical car engine is able to pull off around an efficiency of around like 55% or so. So that's pretty great. But an actual car engine, once you have to start factoring in all the friction resistances, all the pressure, the various turbulence that starts to happen, the sort of randomness that can't be controlled for, actual car engines manage to pull off around a 25% efficiency rate. So efficiency is really, really hard to come by. Most of the energy that we wind up breaking down from our chemical bonds actually just goes to heat. We aren't able to get most of our heat to turn into work, which is a real shame, because if we were able to manage to just double this, we'd be able to do great things with the amount of energy we have. So one of the best things that we could do to get more energy is to be able to just increase our efficiency. But there's this like hard limit to the best efficiency we can get, and that's based on our hot temperature and our cold temperature. And unless we're able to get those really far in difference, more importantly, get a really nice cold sink temperature, you just can't get that great in efficiency because of our Carnot maximum efficiency. So in real life, efficiency is really hard to come by. So an actual car is able to pull off around 25%. So most of the gasoline you wind up burning in your car actually just goes to heating up the air around you. Kind of disappointing, but certainly really interesting. And that's the nature of thermodynamics. A lot of stuff, all the order eventually falls into disorder. It's not exactly the happiest of endings, but you know, that's how things are going to go with time. Entropy is the winner in the long run. We can at least have a long period of order and thought and intelligence and, you know, great complex beings. But in the really, really long end, as the universe runs to its end, things eventually will tend to disorder, and we'll just have complete, you know, fall apart as the universe goes into just hot heat death mode as it breaks apart. But that's a long, long, long time from now. And for our purposes, we can basically forget about that. We're going to have the chance to live long, complex, interesting lives in a nice, cool universe that hasn't seen the long, painful end of entropy yet. So things are good for a long time to come, so don't worry about it. All right. Hope that was interesting. Hope you learned a lot. We'll see you at Educator.com later. Bye.